Okay, in the last lecture, we looked at several basic functions like quadratics and cubics and absolute values, things like that. Now we're going to look at a different class of functions called piecewise defined functions. And essentially the idea is we know how to graph a quadratic. There's a parabola right there. We could graph a cubic. But, well, now it's called a piecewise defined function because now we're going to take those graphs and cut them into pieces. So again, suppose we have this quadratic right here, and we know the domain of this is all real numbers. But suppose for the sake of argument, I wanted this graph, but I only wanted the domain to be all the x's greater than or equal to 0, for whatever reason. I had a specific problem, and I only wanted my x's to be positive. Well, how does the graph change? Well, I'll still get the same y values, but if my domain is only the x is greater than or equal to 0, then take all the x's less than 0 and erase that part of the graph right there. And I essentially end up with half of a parabola. And that's essentially what we're going to do. Take parts of the different graphs that we know and throw them all in the same picture together. One thing I'll say at the outset, when you're graphing these things, if the graph that you get does not pass the vertical line test, then it's not a function. And if it's not a function, then it's not graphed right. So make sure to check yourself as you do these and make sure whatever you graph passes the vertical line test. So, suppose we'll start with this one. F of x equals x squared if x is less than or equal to 0, and x cubed if x is greater than 0. And yes, it looks a little bit odd, but, well, all we really have to do, we know what the x squared graph looks like, so we can graph it, but we only want to deal with the x's less than or equal to 0. So let's see. Normally, the parabola x squared looks like this. But now I want to restrict myself to the x's less than or equal to 0. So now I only care about the stuff on the left. So get rid of all of that, because I don't care where x is greater than 0. One of the tricks that goes along with this, what do you do for this endpoint right here? And the way it works, if you remember when we worked with inequalities and number lines, if you're including the endpoint, you draw a closed circle. If you're not including the endpoint, you draw an open circle. Same idea here. We want this graph when x is less than or equal to 0, which means we want the endpoint when x is 0, so make sure to draw a closed circle there at 0. And there we go. There's my parabola, or half of my parabola. We'll now graph this. If x is greater than 0, we get x cubed. Again, we know what the graph of x cubed is. It looks like this, and then like that, the elongated s. But that doesn't pass the vertical line test. We can see that easily. But that's because we only want this graph when x is greater than 0. So for all the x's less than 0, all of these, get rid of it. And now, well, that passes the vertical line test right there. Keep in mind, at this endpoint right here, that's a greater than 0. We don't want to include that point, so we draw an open circle. But in this case, we would be drawing an open circle right where we already drew a closed circle, so we can just leave the closed circle there. And yes, I know that looks just like a parabola. It's not a parabola. This part is a parabola, this part is a cubic. It's steeper on this side than that side. To maybe make it easier to see, we'll look at a few others. Suppose we have f of x equals x minus 2 if x is less than 0, and 2x plus 3 if x is greater than or equal to 0. Again, we have two parts to our graph, so ultimately graph both things restricted on their domains and put them on the same picture and make sure it passes the vertical line test. For the first one right here, well, that's the equation of a line. That's in slope-intercept form. So the slope is right here, 1. The intercept is -2. So to graph it, well, it's a line with a slope of 1 and an intercept of -2. To graph the line, you can pick several points. You might as well pick the endpoint. Yes, this is defined for x is less than 0. So at this endpoint, we'll draw an open circle, not a closed circle, but use the endpoint as a guide. If you plug in x equal to 0, you get 0 minus 2, -2 down here. Draw the open circle. Now, if you want to plot other points for x is less than 0 to get an idea of the graph, you can. But we know the slope is 1, which means when we go to the left, it goes down. So the graph will just look like that. Line with a slope of 1, and it stops at 0. Now do the other graph. For x is greater than or equal to 0, we get 2x plus 3. But again, that's the equation of a line. That's the slope, that's the intercept. So to graph it, pick a point or two. You might as well pick the end point. When x is 0, I get 3. This is defined for x is equal to 0, greater than or equal to 0. So I'll draw a closed circle at 3 right here. And now again, if you want to plot a few more x values to see what the graph looks like, you can. But this is a line with a slope of 2, so we'll just make it go up like that. We've done everything listed up here, so that should be our graph. The last thing we want to check is the vertical line test to make sure it passes it. But yeah, the only possible problem occurs right here along the axis, but this point is closed and that one is open. It's only defined here, so it's only defined in one place. So it'll pass the vertical line test. One other thing we can do with this graph that you will be doing for homework and on your exam, finding the domain in the range. The domain for these piecewise function is pretty straightforward. It's given to you right here. This is defined for x is less than 0 and greater than or equal to 0. So it's defined for all x's. So that's just real numbers, all real numbers. The range is where this can get tricky, but do the same thing we did before with our other graphs. Just use your arm. Right here, all these y's will get touched. That line will continue down forever. So all these y's will get touched. And it'll stop right here at this point. And when we graphed that, that was the point 0, -2. So the range will be all the y's. Maybe this one, just for fun, we'll do it in interval notation. Ultimately, I don't care which way you write your answers, so we'll do both, just so we can see them. This will go from -infinity, open, up to -2. That's open because that point is open. Union, if you've never seen the union before, it's just a way to join intervals. So just draw the U like that. It means union. And then none of these y's get touched. And then this one does. And again, this was the point 0, 3. And then from here, everything up will get touched by this line because it goes off forever. So this will be closed 3 to infinity. Keep in mind, this is open because that point is open. This one is closed because that point is colored in. We want that point right there. Let's see. We can maybe quickly do one more. So suppose we have f of x equals x squared if x is less than 0, or if x equals 0, and the absolute value of x if x is greater than 0. So now we have 3 parts as opposed to 2, but the idea is the same. Graph each of the 3 parts separately on the same picture and make sure it passes the vertical line test. So, first, for x is less than 0, we get x squared. That's just a parabola, just restricted to x is less than 0. So, draw my parabola at 0. Since that's only defined for x is less than 0, I draw an open circle. That part's done. Now, when x is 0, we get 4. That's actually a point, the point 0, 4. So just color in the point 0, 4. That's that part. That's easy enough. For the last one, for x is greater than 0, we get the absolute value of x. Again, we know the graph of absolute value of x. Starting at 0, we draw an open circle at 0 because it's only for x is greater than 0, which means, well, that point was already open at 0, and now we leave it open. But then over here, we just draw the absolute value graph, which is a line at a 45-degree angle. And now we have my graph. This is the parabola for x is less than 0. This is the point 0, 4. This is the absolute value graph for the x is greater than 0. The last thing we care about, domain and range. Again, the domain is the easiest part that's given to you right here. It's defined for x is less than 0, equal to 0, and greater than 0. That's all possible numbers. So it's all real numbers. For the range, do the same thing with your arm. None of these y's get touched. The first y that gets touched is right here at 0, but it's undefined there. Which means we draw an open parentheses at 0. Open. And now if we look, all of these points will get touched. The parabola keeps going and the absolute value keeps going. So from here on out, every other y value gets touched. So this will go up to infinity. Open. And now we have our domain and range. You're going to do a lot of these for homework. Like I said, do each graph separately, put them all in the same picture, and the last step, make sure your graph passes the vertical line test. For us, the only possible problem is right here along the axis again, but again, this is closed and that's open, which means a vertical line would touch this one, but not that one, so we're good. Vertical line only touches it once. It is the graph of a function.